Hello friends, welcome to UGC EPG Pathshala. I am Dr. Lubna Siddiqui, Assistant Professor, Department of Geography, Jamia Millia Islamia, New Delhi. Today I am going to discuss about the module Multiple Linear Regression Analysis, Simple and Stepwise Regression, which comes under the paper Quantitative Techniques in Geography. Now, regression analysis. Ultimate objective of any research is to understand the causes behind a process with objective to control it as per our requirement. Knowledge of the degree and direction of correlationship between a dependent and independent variable alone is not sufficient to help in this regard unless it gives the mathematical equation giving the relationship between them. Through this form of causal relationship, that is cause and effect relationship, we can evaluate the effect of different independent variables, also known as determinants, on the dependent variable, and can also make projections of the dependent variable for some projected future values of independent variables, etc. Regression analysis helps us in identifying the above mentioned functional form of relationship. If we have only two variables to analyze, that is one dependent and one independent variable, the regression is known as bivariate regression. However, if the number of independent variables are two or more, it is known as multiple regression analysis. Explanation of regression analysis becomes very complicated if we directly start from multiple regression analysis. It is easier to explain bivariate regression analysis first and explain multiple regression as its extension. Now, bivariate regression analysis. Functional form of relationship between two variables is best explained by taking a straight line on a graph paper having y coordinate and x coordinate. The y and x coordinates of these points will be related by a general functional form as y is equal to a plus b x plus epsilon. In any such equation of a straight line, a is known as intercept of the line, that is the value at y axis where the line will cut y axis, value of y after putting x is equal to 0. B, the rate of change in y with respect to x, is known as the slope of the line, and epsilon is known as the error, and the relationship y is equal to a plus b x is known as linear relationship as it relates to a line only. Thus, if we refer to any specific straight line, we can specify it by fixing the values of a and b. However, most of the bivariate data from social sciences through following a linear pattern of relationship will not exactly fall on a straight line. On a scatter plot of such data, the points may cluster around a straight line and give some deviations on either side of the line as indicated by epsilon. In such cases, the line around which the points cluster could be identified to give the relationship between two variables x and y. Here the values of y and x will fall on the line and relationship between them will be exact. Actual relationship between values of y and x falling around the line will only be approximate to it. The value of the coefficient of correlation will give the direction and the degree of such linear relationships. The equation of the line passing through the scatter plot will give the functional form of linear relationship between the two variables. Now, principle of least square. As any number of lines can be drawn through a given scatter plot of a set of bivariate data, we have to develop a principle to select an optimal line. A statistical theory has developed the principle of least square to govern the choice of such an optimal line. Consider the following values of x and y variables and their scatter plot. As is clear from the above graph, a line is drawn from the middle of the scatter in such a way that almost half of the points fall above it and half below it. Once the line is drawn for every given value of x, we have an estimated value of y from the line apart from its given value. The difference between given value of y and the estimated value of y is known as the residual or error. For example, in the above case, for first given value of x is equal to 2, the given value is 20, whereas the estimated as given by line is 32. The difference is 32 minus 20 is equal to 12. In the second case, for given value of x is equal to 4, the given value of y is 44 and the estimated value is 40, and the difference in the second case is 40 minus 44 is equal to minus 4. Likewise, the residuals or errors for all other observations can also be calculated. For total error, the sum of these residuals will be misleading, as minus residuals will cancel the plus residuals. Residuals are therefore squared and then added to give the total error. If we draw different lines, we will get different values of the sum of the squares of residuals, one with every line. Ideally, we will choose the line as optimal, which will give us minimum value of the sum of the squares of residuals. This principle is known as principle of least square, and the line will be known as regression line. In practice, we do not take several lines, but take the help of differential calculus from mathematics, which suggests that the slope b, which is also known as the regression coefficient of such an optimum line, will be b is equal to summation in bracket x minus x bar bracket close in bracket y minus y bar bracket close upon summation x minus x bar into 2 is equal to summation x y minus in bracket summation x summation y in bracket close upon n upon summation x into x minus in bracket summation x bracket close in bracket summation x bracket close upon n, and the intercept will be a is equal to y bar minus b x bar. After computing the regression coefficient, the analysis also focuses on its magnitude. We test the hypothesis that whether the value of b is so very close to 0 or not. In other words, we test the hypothesis that can its actual value or population value may be considered as 0. For testing such a hypothesis, we use t-test, according to which, under the following assumptions, the variable epsilon is a random variable distributed normally, mean value of epsilon is 0, variance of epsilon is constant for all value of x. If there are more independent variables, all are independent to each other, that is, there is no multicollinearity among the independent variables. A computed values of b will follow t distribution with n minus 2 degree of freedom, that is, t is equal to b upon s e into b, where s e b is equal to sigma mu upon under root summation x into x minus summation x into summation x upon n. Sigma mu square is equal to total sum of square minus explained sum of square upon n 2. Total SS is equal to summation y into y minus summation y into summation y upon n is the sum of a square of deviation of y from its mean or variations in actual values of y, and explained SS is equal to B summation x into y minus summation x into y upon n is the sum of square of deviation of estimated values of y from its mean or variations in the estimated values of y. As estimated values of y are values found on the line, their variations will always be less than the actual values of y. Objective of any regression line is always to get the estimated values of y, giving variations as close to actual values of y as is possible. The ratio of explained sum of square to total variations in y is therefore an indicator of the quality of any regression model and is known as coefficient of determination and denoted by r square, given by r square is equal to explained sum of squares upon total sum of squares. The value of r square will vary between 0 and unity. If a value is found to be say 0.75, will mean that of the total variations in the dependent variable y, 75% are being explained by the independent variable x chosen here. Again, to test the statistical significance of r square, we have f ratio test as f is equal to r square in bracket n minus k upon 1 minus r square into k minus 1. K minus 1 n minus k degrees of freedom. Example, from the data as given below, we can compute the regression coefficient and the intercept of the regression line as shown below. Using the above formulas for regression coefficient b and the intercept a, b is equal to 10,701 minus 120 into 756 upon 10 upon 1830 minus 120x 120 upon 10 is equal to 4.177, and a is equal to y bar minus b x bar is equal to 756 upon 10 minus 4.117 into 120 upon 10 is equal to 25.46. Regression analysis also requires calculation of a standard error of b to carry out the statistical test of significance to assure that the regression coefficient b is not very close to 0. Total SS is equal to summation y into y minus in bracket summation y bracket close in bracket summation y upon n is equal to 66,100 minus 756 into 756 upon 10 is equal to 8,946.4. Explained SS is equal to b summation x into y minus summation x into y upon n is equal to 4.177 into 10,701 minus 120 into 756 upon 10 is equal to 4.177 into 1629 is equal to 6804.33. Sigma mu square is equal to 8946.4 minus 6804.33 upon 8 is equal to 267.71, or sigma mu is equal to under root 267.71 is equal to 16.36. SEB is equal to sigma mu upon under root summation x into x minus summation x into summation x upon n is equal to 16.36 upon under root 1830 minus 120 into 120 upon 10 is equal to 16.30 upon 19.75 is equal to 0.83. T is equal to b upon SE into b is equal to 4.177 upon 0.83 is equal to 5.032. R square is equal to 6804.33 upon 8946.40 is equal to 0.761, and f is equal to r square n minus k upon 1 minus r square into k minus 1 is equal to 0.761 into 10 minus 2 upon 1 minus 0.76 into 2 minus 1 is equal to 25.47. F value for df is equal to 1, 8 in bracket 2 minus 1, 10 minus 2 given in the table are 16.86 for 1% and 5.32 for 5% levels of significance respectively. Our calculated value is found to be significant even at 1% level of significance. Thus, we can say r square is statistically significant from being 0. In other words, we conclude that the independent variable is explaining the dependent variable in a substantial way, not in any random way. Multiple linear regression analysis through matrix algebra. Multiple regression analysis is an extension of bivariate regression analysis in which we have one dependent variable and two or more independent variables. In multiple regression analysis, the regression model for p variables and n number of observations, that is y1 is equal to b1 plus b2 x21 plus b3 x31 plus bp xp1 plus epsilon I, where I is equal to 1, 2, 3 n. y2 is equal to b1 plus b2 x22 plus b3 x32 plus bp xp2 plus epsilon 2, and yn is equal to b1 plus b2 x2n plus b3 x3n plus bp xpn plus epsilon n. The above set of equations can be written in matrix form as below, where y, b and epsilon are columns vectors of p into f dimensions and x is a matrix of n into p dimensions. Here, convention of writing row number first and column number next has been interchanged to suit to the equation formation. Applying the principle of least square to the above set of equations, we can get solution vector beta giving the estimated b1, b2 and bn values of the constants of the regression line passing through the scatter of points as beta is equal to x into x 1 minus 1 into y. Examples given. We can carry out the estimates of regression coefficient in the following manner. We can arrive at the same results using the method of normal equation from ordinary algebra. However, if the number of variables and number of observations are large, as mostly is the case in geographical research, it is quite useful to use matrix method as shown above. Advantage with matrix method is that we can use some computer packages dealing in statistical analysis like SPSS, STATA and SAS etc. Like bivariate case, we can also carry out the t-test and work out f ratio for a multiple regression analysis also, for which the values are given as total SS is equal to summation y into y minus summation y whole square upon n is equal to 120 minus 20 into 20 upon 5 is equal to 40. Explained SS is equal to beta xy minus summation y whole square upon n is equal to minus 0.0922 1.7329 minus 0.4690 20 80 56 minus 20 into 20 upon 5 is equal to 119.1885 minus 80 is equal to 39.1885. R square is equal to coefficient of determination is equal to explain SS upon total SS is equal to 39.1885 upon 40 is equal to 0.9797. sigma square mu is equal to total SS minus explained SS upon n minus p is equal to 40 minus 39.1885 upon 5 minus 3 is equal to 0.8115 upon 2 is equal to standard error of beta 1 is equal to under root sigma 2 mu into ith diagonal value of inverse x bar x. Standard error of B1 is equal to under root 0.4057 into 1.3135 is equal to 0.7300 or T1 is equal to 0.0922 upon 0.7300 is equal to 0.1263. Standard error of beta 2 is equal to under root 0.4057 into 0.1101 is equal to 0.2144 or T2 is equal to 1.7329 upon 0.2144 is equal to 8.1970. Standard error of beta 3 is equal to under root 0.4057 into 0.3389 is equal to 0.3708 or T3 is equal to 0.4690 upon 0.3708 is equal to 1.2648. As tabulated, value of T for 3 degrees of freedom at 5% level of significance is 2.920 and at 1% level of significance it is 6.695. We conclude that only the value of T2 is found to be significant at 1% level of significance. Thus, the only regression coefficient b square related to variable x1 has shown a significant effect on y, which is 1.7329 for a unit change in x1. Intercept b1 and the regression coefficient b3 related to variable x2 and the intercept are found to be insignificant even up to 5% level of significance. F is equal to r square n minus k upon 1 minus r square k minus 1 is equal to 0.9797 into 5 minus 3 upon 1 minus 0.9797 into 3 minus 1 is equal to 1.9594 upon 0.010 is equal to 195.94. F value for df is equal to 2, 3 minus 1 is equal to 2, 5 minus 3 is equal to 2 is 99.0 at 1% and 19.0 at 5% levels of significance respectively. The test of significance also reveals that the two independent variables x1 and x2 explain the variations in the dependent quite substantially. Now, stepwise multiple linear regression analysis. Stepwise regression analysis relates to evaluation of the relative efficiency of independent variables in explaining the dependent variable when the variables are added or deleted to the model one by one in several steps. It has two approaches, forward and backward. In forward stepwise regression, we start with one most important variable followed by the second, third and the least important variables. In backward approach, we start with all the variables and keep on excluding variables one by one and proceed in the reverse direction until we reach the optimal position. Now, need for stepwise regression analysis. One of the important assumptions of the test of significance of OLS regression analysis is that independent or explanatory variables are independent of each other. This assumption is known as assumption of absence of multi-collinearity. Sometimes this assumption is violated and variables are found to be collinear where independent variables show significant intercorrelation among themselves. In such cases, there is some overlap in the explanatory power of the two or more collinear variables. Higher the relationship between the variables, higher will be the overlap. For example, if a variable is explaining 40% of the dependent variable and another variable related to it is explaining 30%. When these two variables are taken together, they may explain 70% of the dependent variable provided both the independent variables are independent. However, if they are collinear or correlated, they will explain less than 70%. Suppose these two variables together explain only 50% of the dependent variables, it will be due to the fact that what second variable is contributing 20% of it has already been explained by the first variable. Second variable has now only 10% contribution to explain in addition to first variable. In the absence of the first variable, however, second variable will have a higher explanatory power. In ordinary regression equation, we will not have any idea about this complication arising due to the problem of multicollinearity. Computer programs have been developed to tackle this problem. Stepwise regression analysis is one such program. In any regression model with some r square, if more variables are added, the value of r square will always increase, either the variable in positively or negatively related to the dependent variable. In a stepwise approach of a regression analysis, independent variables are subsequently added to the model one by one until the criterion of variable addition is not met. The sequence starts in such a manner that in first step it gives regression line with one independent variable, choosing from all the independent variables the one which gives maximum r square. In the second step, it adds a one more independent variable to the model which adds maximum value to the existing r square. Likewise, in third step, one more variable is added and so on. Every time the addition to r square due to new variable will be less than the previous value, and the value of f ratio will also change. In stepwise regression analysis, we can fix a criterion of adding a new variable. Generally, it is done by choosing the probability level of the changed value of f due to the addition of new variables. In most of the cases, if the probability exceeds the fixed limit, say 0.05, the variable is not added to the model. R square adjusted is designed in such a way that with the increase of every new variable, it will decrease unless the new variable causes a significant increase in the value of r square. In stepwise regression analysis, we keep on allowing the addition of new variables until r square, that is adjusted, increases. After few steps, though r square will continue to rise, r square adjusted will start decreasing, indicating the fact that addition to r square is not big enough to be retained in the analysis. Now, example. Declining sex ratio in India is a big concern of the society. There are a large number of factors behind it. In the following example, for the sake of simplicity in explanation, we have taken few of them and used a stepwise regression analysis to explain the variations in the sex ratio in the 50 districts across Madhya Pradesh for 2011 with the help of the following variables. Sex ratio, that is females per 1000 male, variable 1. Growth rate of population during 2001 and 11 in percentage, that is variable 2. Levels of literacy in percentage, that is variable 3. Population density per square kilometer of area, that is variable 4. Female work participation rate in percentage, that is variable 5. Using SPSS, when data given in annexure was subjected to the bivariate correlation and stepwise regression analysis, following results were obtained. First, it gives the intercorrelation matrix of each variable with other variable given in table 1 given below. It also identifies the level of significance at which these coefficients of correlation are significant. The table shows that the dependent variable x ratio, that is variable 1, has an insignificant negative correlation coefficient with the variables. Rate of population during 2001 and 11, that is variable 2, and levels of literacy, that is variable 3, and a significant negative correlation with the variable of levels of literacy, that is variable 3. It is found to be significant at 5% level of significance. The intercorrelation matrix also shows that the dependent variable has a strong positive relationship with the variable of female work participation rate, that is variable 5, significant at 1% level of significance. Please note that two-tail test means that a value of coefficient of correlation could be 0, that is it could be greater than or less than 0. One-tail test will mean that coefficient of correlation could be either less than 0 or more than 0, that is either greater than 0 or less than 0. The diagonal elements of an intercorrelation matrix are always 1, indicating the correlation of a variable with itself is perfect, and coefficient of correlation will be therefore 1. Table 1 shows the intercorrelation matrix. The intercorrelation matrix given above suggests reasonable justification for the choice of the explanatory or independent variables to explain the variations in the values of the dependent variable sex ratio. The above matrix of intercorrelations also suggests the overlap among the independent variables. The matrix shows intercorrelations among independent variables also. Fourth variable of the density of population has a strong positive relationship significant at 1% level of significance with the second variable of growth rate of population and third variable of literacy, which has a strong significant positive relationship with the fifth variable of female work participation rate. Female work participation rate also has a strong negative relationship with the density of population. The intercorrelation among independent variables suggests that there exists some multicollinearity among them, and an ordinary regression analysis will not be the optimal regression equation. A stepwise regression is likely to give better results by excluding the redundant variables and retaining only those which add a higher value to R square as explained above. It will also give the order of the efficiency with which each of the independent variable explains the dependent variable of sex ratio. A stepwise regression analysis will give different models by adding independent variables one by one sequentially. The criterion to add the new variable is in terms of probability of its f value being less than 0.05 or 5% as is shown in table 2 given below. We can also change the probability to 0.10 or 10% to allow more variables to enter into the analysis. In the present example, the result given in table 2 given below shows that only two variables, that is female work participation rate, which is variable 5, and density of population, which is variable 4, are sufficient to be retained in the multiple regression analysis. Other variables, population growth rate, that is variable 2, and level of literacy, that is variable 3, are not found to be explained much the variation in the sex ratio of the districts of Madhya Pradesh. Their part of explanation is already explained by first two variable, that is female work participation rate or variable 5, table 2. Table 2 shows the criteria for choosing the independent variables stepwise regression analysis. The summary results of the two steps of the regression model will follow in the computer output as given below in table 3. Model 1 given by the first step shows that only one variable, that is female work participation rate, that is variable 5, alone explains the sex ratio quite effectively. It explains 70.6% variations of the sex ratio across 50 districts of Madhya Pradesh as per the data provided by the Census of India. The next variable which could be included in the model is the population density, that is variable 4, which could add to the explanatory power of the model only 3.6%, as the value of R square could rise from 0.706 to 0.742 only. R square, that is adjusted, could also rose from 0.700 to 0.731 only. Another two variables could not qualify the criterion of entering into the analysis due to multicollinearity. Once the model is chosen, the main results follow. These include regression coefficient of the selected variables, their standard errors, t statistics, and the level of their significance. These results are also given in table 4 below. Table 4 given above show the regression coefficients on standardized form as well as in standardized form. Unstandardized coefficient relate to the data as provided in the computer input and also gives the value of the intercept as constant. Computer also converts the given data into their standard scores and give corresponding regression coefficients as standardized coefficients. The purpose is to bring the data to a standard form of 0, mean and unit standard deviations. In standardized form, when the mean of all the variables is 0, intercept is not given as it also becomes 0. Standard error and t statistics of the regression coefficient, however, in both the cases remain the same. The results of the above table show that as it is a unit change in the employment to female will promote an increase of 4.214 rise in the sex ratio, whereas the density of population does not show much impact on the sex ratio. A change of 1 person per square kilometer will bring a change of only 0.063 change in sex ratio. It is important to note that female work participation rate varies within a narrow range from 8.4 in Bhid to 52.9 in Dindori. Density of population has quite big range of variation from 855 in Bhopal to 94 in Anuppur. These variations have been standardized by converting all the three variables into their standard scores. As a result, the gap of 3.832 between the regression coefficients of unstandardized form, that is 4.214 minus 0.382 is equal to 3.832, is reduced to 0.734 between the same in unstandardized form, that is 0.954 minus 0.220. The proportion of the two has also been reduced from 11.03 is equal to 4.214, 0.382 to 4.33 is equal to 0.954 upon 0.220. I hope you have understood the concept of multiple linear regression analysis, simple and stepwise regression. See you next time. Thank you.